Well, hello. I wanted to describe the solar system basically in three parts. I thought it'd be convenient to divide it up into outer solar system, middle solar system, and inner solar system. And I also thought there's no reason to do the whole lot at once, right? It just makes a big long video. I'll just divide it up into three little videos that will be more easy to watch if you want to watch them at all. It's totally up to you whether you do or not. So the first one is outer solar system. I want to talk about these things: Kuiper belt, unseen planets, or the possibility thereof, and the Oort cloud, followed by a final thing on birth constraints of the solar system. And I want to do it from an observational perspective, and I want to do it by simplifying everything as we go along. There's enormous complexities and confusion and stuff that we just don't need to get into in this lecture. So let's start with the Kuiper belt. So the Kuiper belt is a region beyond Neptune. It's 30 AUs and more, also known as the trans-Neptunian belt. It's very special in the solar system, not just because it's the most recently discovered largest piece of the solar system, but because it's a place where the temperatures are very low, black body temperatures, 40 Kelvin or something like that. And as you know, chemistry varies. The rate of chemical reactions goes with the exponent, e to the power of temperature. And so these very low temperatures essentially prohibit chemistry. There is radiation chemistry where cosmic rays hit the surface of a Kuiper belt object and do things. But essentially the normal kinds of chemistry that we worry about in the inner solar system do not happen in the Kuiper belt objects unless they're very large. The large ones can be self-heated by the binding energy, the gravitational binding energy of their formation, and also by radioactive decay, just as in the asteroid belt. But the small ones probably not. So these are bodies which are cold. They can preserve ice from the beginning of solar system time. They're full of primordial ices. And in fact, we know the Kuiper belt is the source of the short period comets, the Jupiter family comets. And we know that those have a lot of ice in them. Maybe 20, 30% of the mass of a comet is in the form of ice, some kind of a volatile material. So that comes pretty much directly from the Kuiper belt, as we'll see in just a moment. So Kuiper belt is really great because it's cryogenic, it's very cold. It's a remnant of the formation epoch of the solar system. It provides us with a record of formation conditions and evolutionary processes that have shaped the Kuiper belt since it formed. It's astonishingly big. It's 1,000 times the mass of the asteroid belt. And it also occupies a volume, 1,000 times roughly the volume of the asteroid belt. And so the density is not very different from the density of asteroids. That means that there is some collisional processing. But as far as getting primitive material, as far as finding a kind of a primordial cold place in the solar system, Kuiper belt is it. And so scientific interest in the Kuiper belt is very, very high. Now, I thought about different ways to present this. In the end, I think the best way is just to show you data. We have about 3,000 known Kuiper belt objects. Roughly half of them have pretty good orbits. To keep this diagram simple, I'm showing you just the first 1,000. So this is semi-major axis against orbital eccentricity, circular orbits at the bottom, parabolas at the top. First observation is that the distribution of dots, each dot is a KBO, the distribution of dots is highly non-uniform, okay? And in fact, it shows immediately that Kuiper belt objects are divided up into a bunch of distinct groups, each of which has special significance, we think, for the origin of the solar system. So this was not predicted. These groups were not predicted. They were just discovered. The whole lot is just a result of staring at the sky and seeing what you can see. Okay, so what do we have? Well, we have this diagram that is essentially the basis for modern solar system dynamics. And the reasons for this are several. I think it's fair to say, don't mean to insult anybody, it's fair to say the objective of solar system dynamics for the last 20, 25 years has been entirely, almost entirely, to understand the distribution of dots in this diagram. Why does the solar system out there look this way? So let's go through and talk about different parts of the Kuiper belt that we have known about now for, I guess, 25 years, just over 25 years. First of all, there's a kind of a clump of bodies with small eccentricity on the order of 0.1. So the difference between the outer, the aphelion and perihelion is roughly 10% of the radius. And the orbit radius is something like 40 something AU, 43 AU. So those are the classical Kuiper belt objects. I called them classical because when they were discovered, you know, in the back of my mind, probably in the backs of many other people's minds, Kuiper belt is like the accretion disk of the sun. And in an accretion disk, the velocities between particles are damped down by collisions. They've become very small, so the inclinations are very small, the eccentricity is very small. It becomes like the rings of Saturn. I thought the Kuiper belt was going to be like the rings of Saturn, and the classical objects were closest to that. Although, in fact, we now know that the correspondence is not very close at all. The velocity dispersion amongst the Kuiper belt objects is actually quite large. It's about, on average, 1.5, 1.7 kilometers per second. So when Kuiper belt objects collide, they actually erode, they make dust. They don't stick together and get bigger. So we're not in the growth phase anymore. It's not any longer an accretion disk. It's the product of an accretion disk, but somehow the velocity dispersion in the Kuiper belt everywhere has been pumped up by something. And that's a major subject of dynamical interest. Now it's obvious you have all these Kuiper belt objects in vertical lines. Those turn out to be resonances. So we have to talk about resonances very briefly. The one on the left, I shouldn't really have plotted that, but I did. It's the resonance with one-to-one resonance with Jupiter. So those are Jupiter Trojans that we'll come to in the middle lecture. There are also Neptune Trojans, so that's one-to-one at 30 AU. These numbers are, of course, just the ratio of the orbit period of the body to the orbit period of Neptune. And the idea is that Neptune is the big guy out there. It's got all the mass and all the gravity. And so Kuiper belt objects have to adjust their orbits in order not to be destabilized by gravitational perturbations from Neptune. So in the case of the resonant objects, the strategy they use, treating them as sentient beings for now, the strategy they use is to stay away from Neptune at all times by using a kind of a phase protection. So even though they can have eccentric and do have eccentric orbits, and even though their perihelion can be inside Neptune's orbit, they're smart enough to know that they can only dip inside Neptune's orbit when Neptune is far away, at a big angle away. So they're phase protected from close encounters with Neptune, and therein lies the basis of their stability. The classical objects, on the other hand, just have circular orbits, so they don't get close to Neptune anyway. Their perihelion is already very far away from Neptune, so they're stable for that reason. So many, many, many resonances have been identified, and the identification of the resonances probably is one of the biggest scientific impacts of the Kuiper belt. After knowing that there is a Kuiper belt, the identification of the resonances is super, super important. Why is that? Well, you can see that the resonances are more occupied than you would expect by chance. If you just threw objects, you threw grains of sand or rice or something on this diagram, you know, the chance that they would line up in these resonant locations is negligible. It's not going to happen. So they're not due to chance. What are they due to? The best and pretty much the only idea is that they're caused by the radial migration of the planets, in particular, the outward migration of Neptune by several AU, maybe 5 AU, maybe 10 AU, basically pushing the resonant locations through pre-existing disk of material, catching objects as the resonances go by. So the key thing is the resonant objects being overpopulated, as we see, is evidence for planet migration in the solar system. And this was a staggering realization because it changed our perception of the evolution of the solar system in radical ways. And in particular, it opened Pandora's box because it made the solar system change from this boring clockwork system where the planets just go around the sun and they always have the same radii and they always have the same orbit period and everything is the same this year as 1,000 years in the future, 1,000,000 years in the future, 1,000,000,000 years. It doesn't make any difference. Nothing ever changes. It's boring. To a system in which the interactions between planets can be very different as a function of time, allowing the possibility of extreme events like resonances between the planets, as described by Nice model, whatever the Nice model is. So the idea is that solar system dynamics was simply revolutionized, and it's become a very exciting and active field in the last 25 years because of this diagram, because of these discoveries out there beyond Neptune. So what else have we got? Well, we've got that band of objects. That band was discovered a little bit after the Kuiper belt. The first one was found in 1997. but now we have hundreds out there in what's called the scattered disk or the scattered Kuiper belt object population. These are bodies that turn out to have a perihelion within 10 AUs of Neptune. So they're affected by the gravity of Neptune, but not very much and only a perihelion. They get a kick every time they go around the sun, a perihelion, orbit period, maybe 1,000 years or something like that. They get this little kick from Neptune, and that can pump up their eccentricity and send them off. They random walk up this arc off to the right. If they go out to very, very large aphelion distances, perhaps they can be detached from the solar system by the external perturbations from passing stars and so on. So the scattered Kuiper belt is interesting. It turns out to be the origin of the short period comets. That's where they come from. They're objects that are lost from this scattered population by scattering events with Neptune. If you look out beyond the scattered Kuiper belt, you see a few objects which are sufficiently far from Neptune at all times. Their perihelion distances are never closer than 15, 20 AUs from Neptune, that we cannot imagine how Neptune has any significant dynamical effect on them. And that raises the question of how they got there. If Neptune didn't kick them out there somehow, how did they get there? And we don't know the answer, but there are several speculations about how that might have worked, and we'll talk about those perhaps a little bit later. And then objects that are not ejected from the solar system by interactions with Neptune can be injected to the inner solar system. And we have a different name for those. They're the same kind of object, but we call them Centaurs. And there are different definitions of Centaur. We'll probably come to that later, but Centaur is an object that has recently left the Kuiper belt. And we think that they have lifetimes in the Centaur region, like tens of millions of years, maybe, sometimes 100, sometimes 1 million years. The lifetimes are limited by strong interactions with the giant planets. Remember, Jupiter's at 5, Saturn's at 10, Uranus is at 20, and Neptune is at 30 AU. So once your orbit dips across the orbits of giant planets, then you have the potential for strong interactions and your lifetime is short. So that entire diagram is an observational diagram. It's all discovery, zero prediction, but it's the subject of intense work to try to understand why the solar system is like that. It's a really big deal. Now, when you look close up, it's more messy than I just told you. It's more messy than I just pretended. So here's a zoom in to part of the Kuiper belt. And you can see that we see the resonances, the vertical things are still there. We see the scattered Kuiper belt objects, that diagonal band is still there over on the right. The classicals are still there. It's kind of a cluster about 43, 44 AU with small eccentricity, but they're all blended together. And it's hard to say which one is which in certain parts of that diagram. So the truth is, we can't disentangle them without doing more work, which means basically integrating the orbits to figure out which, if any, of those groups the objects belong to. So I just show that to remind you that it's not as clean cut as people often pretend. In fact, everything when you look in detail is kind of a mess. Certainly that's the case with the Kuiper belt. Also, I wanted to point out that there does seem to be an edge to what we would call the classical Kuiper belt objects at about 47 AU, which is where the 2-to-1 mean motion resonance, that black line on the right is at 47, that's 2-to-1. And that was a big surprise. That was actually refuted. So a bunch of people told me that that's not real. And some people told me that's not real because it didn't fit their models. Some people told me it's not real because it didn't fit their observations. It seems to be very real. It persists, and it represents an outer edge to the classical Kuiper belt component, which itself is unexpected and quite interesting and a subject of research as well. The whole thing, plotting semi-major axis versus inclination, looks like that. The deal, what you should learn from that diagram is most objects are prograde. They go around the sun in the same direction as the planets. The average inclination in the Kuiper belt is like 12, 15 degrees, but it depends on which dynamical subpopulation you're looking at. The resonant objects are a bit bigger than the classical objects, and the scattered objects are bigger, and so on. There are some retrograde objects, so everything above the dashed line is going around the sun backwards. The origin of those objects is a subject of research at the present time. There are different ideas. Many of them, I think, certainly you see most of them are compacted at small semi-major axes. Many of them are just long period comets that don't really belong on this diagram, but they're there. But it is possible to transform prograde orbits into retrograde orbits. apparently by complicated dynamical interactions. So some of them are modified Kuiper belt objects. I also wanted to point out that we don't have perfect knowledge, right? Nothing is perfect. Observations certainly are not perfect. We are very limited by observational biases. And the biggest one, the easiest one to understand, is a sensitivity limit bias, which basically means we have observations of the sky down to a given flux density limit, a given brightness limit. And so we can't see really faint things, okay? And what that means is there's a bias against the detection of small objects because small objects are faint. And that bias grows in importance as the distance from the sun increases, and it grows quite dramatically. So at the distances of the classical Kuiper belt objects, the CKBOs, we're pretty good at seeing objects that are like 100 kilometers across and bigger. For the Centaurs, we can see smaller objects because they're closer. So we can see 10 kilometers and 10, 20, 30, 40 kilometer sized objects in abundance. But anything beyond the classical Kuiper belt object, we struggle to see, okay? We struggle to see. And so we don't really know much about the 10-kilometer objects or the 1-kilometer objects in the Kuiper belt at large distances because they're just too faint for us to see. So that bias is shown in a different way here. It's absolute magnitude on the vertical axis, big objects at the top, small objects at the bottom, semi-major axis on the horizontal axis. And what you can see is a red line, which is inverse heliocentric distance to the 4th power. And that's the inverse square law twice. Inverse square law from the sun out to the object, and then inverse square law scattering the radiation back to the observer sitting here on the Earth. So you get this inverse 4th power dependence. And you can see it sort of fits the data out to about the classical Kuiper belt object, but then beyond that, the points fall in a horizontal line, not an r to the -4 line. And that's because we can only see those distant objects when they come into a perihelion that's not too big. When they come into a perihelion of 40, 50, 60 AU, we can see them. But most of the time, in most of their orbit, we can't see them. So what that means is we're seeing a tiny fraction of a bigger population of bodies. We just see the ones that dip in close enough to be detected in our surveys, given their current sensitivity. And we're absolutely insensitive to similar objects with the same semi-major axis, but smaller eccentricities, because they don't come close enough and we can't see them. So the details don't matter. The point is the observations are highly, highly biased, and that will be a theme for this talk and the others. So very quickly then, classical belt, small eccentricity, mostly between the 3-2 and 2-1 mean motion resonances. They're long-lived because they avoid Neptune, because they don't have big eccentricities, and the orbits are big enough that they could stay away. The resonant Kuiper belt objects, super important for understanding planet migration and therefore the evolution of the solar system, because the resonances are only populated, we think, because of the past existence of planetary migration. They avoid Neptune because they're kind of phase protected from ever meeting Neptune, even as they go around the sun, even as they can cross Neptune's orbit. So resonant objects, super important for evolution of solar systems. Scattered objects, super important for supplying the short period comets. These are high eccentricity bodies with the perihelion within reach of Neptune. They're scattered periodically by Neptune. Their evolution is chaotic. They have a lifetime of a billion years. So the population has decreased by a factor of several since they were formed. This is the source region for the short period comets, we think. The detached objects are a bit more mysterious. They're probably not kicked around by Neptune because they never get close to Neptune, at least now. They're probably moved around by something else. We don't know what. There are various interesting models in circulation. And I forgot to say the classical Kuiper belt is kind of divided into 2 bits called dynamically hot, dynamically cold. They're both kind of cold relative to the scattered objects. For example, they have small inclinations and small eccentricities. The cold classical Kuiper belt objects are thought to be the most primordial bits of the primordial Kuiper belt. And in fact, the cold classical belt in many ways is the hardest part of the Kuiper belt for various dynamical models to explain, because these models often involve scattering and crazy events in the solar system that would disturb the cold classical Kuiper belt orbits unless you're very, very careful. The mass of the whole thing is about 1/10 of an Earth mass. So, that's pretty pathetic. Given the vast volume of the Kuiper belt, that's a very small mass of material. There's probably significantly more mass in objects at larger distances that we can't see, but because we can't see them, and because we don't trust, because we don't have any real ability to predict what's out there, we don't know what the actual mass of the Kuiper belt is. But it's unlikely to be, for example, much more than an Earth mass of stuff out there. It's pretty small. And so that raises this question of, how could you form objects given such a small mass in such a big volume? And the answer is that if the body's formed just by collisional accretion, you couldn't do it unless the Kuiper belt we see is a faint remnant of a much more massive original Kuiper belt. So there's two ideas, basically. One, that the Kuiper belt was originally very massive compared to what it is now, much more than 1/10 of an Earth mass. And that somehow all of that mass was lost except for the remnant that we can now see. Or maybe the Kuiper belt objects were formed somewhere else in a dense place and then were displaced out to where we see the Kuiper belt now. And there's probably a bit of truth in both of those. So the current models have Kuiper belt objects in many cases formed interior to the present Kuiper belt and scattered into the Kuiper belt. But at the same time, we think there's been strong dynamical erosion of the Kuiper belt. There was this idea that maybe we could also lose mass from the Kuiper belt by collisions. You smash bodies together and you pulverize them into dust, and then the dust is dragged away by radiation forces or gas drag or something. That's okay, except it's very difficult to smash up big bodies that we see in abundance in the Kuiper belt. It's quite difficult to do that. And so I think the preference now is for a dynamical erosion of the Kuiper belt rather than a collisional destruction of the Kuiper belt. So if we started with a Kuiper belt mass that we're estimating now as 20 or 30 Earth masses, we have to get rid of that. And dynamics conceivably could do that. But I would point out, 20 Earth masses of solids, given that the ratio of gas to dust is 100 or some number like that, is 2,000 Earth masses. So we've got 2,000 or 3,000 Earth masses of gas in the original protoplanetary disk that we have to get rid of. And I don't know how that happened. Some people think they know how the disk was removed, but that's an area of great interest and an area of research still at the present time. How do you clear the disk? When do you do it? We know that it happened pretty soon, but how is that coupled to the evolution of the star? How is it related? What was the UV flux of the sun in the early times? Was the wind strong enough to blow away all this material? None of this is obvious. There's a lot of hand waving going on, I think, in understanding the early evolution of this disk. Okay, now we do have limits to the amount of craziness that you can have in the Kuiper belt, and the strongest limits are set by the wide binaries. So we've discovered a lot of very loosely bound binary objects in the Kuiper belt, and they basically limit the amount of strong scattering and collisional events and so on that you can have in the Kuiper belt because these binaries would be dissociated. So the fact that they survived places constraints on models that otherwise would not exist. So I wanted to mention that. So again, I said a little while ago, the idea of dynamics really is to try to explain what we've seen in this distribution, the strange distribution of orbital elements in the outer solar system. Models include a lot of assumed parameters. So for example, Nice model, to name one, although we don't know exactly what the Nice model is. It's kind of evolving with time, but it involves strong scattering between planets. Assumes things about the starting locations of planets, their masses, their orbits, the shapes of the orbits, the inclinations and the eccentricities of the orbits, the location and the mass of the initial Kuiper belt, the growth state of the Kuiper belt bodies. We don't want them to accrete too quickly. We want to keep them small so they can exist to provide dynamical friction to circularize the giant planets after the fact. And we don't know exactly how the migration worked. Was it slow? Did Neptune scoot out in a majestic, slow fashion over some long period of time? Did it go out quickly? Was it jumpy as it scattered big objects and moved into gaps? we don't know. So these are all parameters for the models that are good because they allow you to adjust the model to fit the observations, but are bad because you have to wonder about, are these reasonable assumptions or not? And do they represent anything that was ever true? So the models turn out to be, in many cases, very, very good at fitting the observed properties of the solar system. It's quite spectacular. The trouble is they're not so good at offering useful, observationally testable predictions. And that's just an artifact of a model with a lot of parameters, okay? But that's where we are. So many people are left wondering, how do we move forward? And the name of the game really is to make models that fit the data, that don't seem to be too crazy, and try to make a prediction of something that somebody can observe in the future. But it does raise the question that you should always keep in your mind: how do we know what is true? And I'll discuss that a little bit later. Now, let me just jump on to unseen planets. There is good reason to think that there might be unseen planets in the outer solar system. And these, when we're talking about unseen planets, we mean some big thing, like bigger than an Earth, probably 4 or 5 Earth masses of planet out there. So what are the good reasons? Well, first of all, when we look at other stars, we do see such things. So we do see planets in large eccentric orbits around some other stars. And we think that they get there by scattering events. So they get there by one planet scattering off another planet, similar mass, and during the scattering event, one is shot out and the other one goes into a more tightly bound orbit around the star. That could have happened in the solar system, and it could have emplaced a planet at large distance such that we haven't seen it yet. That's possible. On the other hand, we have a relatively benign, well-behaved planetary system. The orbits of the planets are pretty circular and the inclinations are pretty small. And it's not clear how you would get such a well-behaved system after you just scattered, a 5 Earth mass or a Neptune or something out to large distances. Also, you need to circularize that planet, otherwise it will just come back in to the inner solar system. So it's not obvious how you would do that, but it's not impossible that it happened because we see that it's happened around other stars. So the real question is, what's the evidence for that? Well, the evidence comes from a reported alignment of the orbits of Kuiper belt objects having a very large perihelion distance. Yeah, so it's shown. This is first noticed by Chad Trujillo and Scott Shepard in 2014. I think I just made these diagrams the other day from new data, but basically it reproduces what they did. So I've plotted the argument of perihelion, which is a measure of the angle of the axis of the elliptical orbit seen from above, against the semi-major axis. And you see that for small, in the top left diagram, for small semi-major axes, you have objects everywhere. So that's a vertical band of red dots. They're everywhere at all angles. But if you look only at the ones with a semi-major axis bigger than 100 AUs, for example, that's shown in the middle panel, then you can sort of, with a bit of imagination, you can see that there's quite a few bodies at the top with argument of perihelion bigger than 240. And there's quite a few at the bottom, argument of perihelion below maybe 60. And there's not many in between. There are not many objects between 60 and 240, okay? So you can see already that this is on the edge, right? So you need some kind of statistics, but you should be careful because whenever people start to talk about statistics, there could well be something funny going on. People use statistics to prove things that are not obviously true, that are not visually true. So we need to do some kind of a statistical test on this thing, but we can do that easily, okay, very trivially. So for example, let's take the argument of perihelion from 60 to 240 degrees, okay? So that's 180 degrees. 240 minus 60 is 180. That's a half of a full circle, 180 compared with 360. So if we just threw bodies randomly on this diagram, we would expect half of them to be between 60 and 240 in argument of perihelion, and the other half to be in the other part of the plot, okay? So in a sample of 22, if you count those red dots, there are 22. In a sample of 22, we'd expect 11 to be between 60 and 240, when in fact we only have 4. So basically you've got 2 cups. You've got the cup here representing angles from 60 to 240, and you've got the cup here representing all the other angles, and you drop things randomly into those two cups. What are the chances that you would get only 4 in this cup and the other 18 would be in this cup? So that's just a binomial theorem problem. Trivial. The answer is about 0.002, so 0.2%. So it's not that likely that you would end up with only 4 in the 60 to 240 bin. So that's basically the argument that lies behind this claim that there might be a planet in the outer solar system. It's a 3 sigma kind of result, isn't it? Well, actually, no. So it's further modified by the need to incorporate observational bias. So once again, we have different kinds of bias in this plot, connected with the inability to map the whole sky uniformly from the ground. Yeah. So we are not uniformly sensitive to objects independent of their argument of perihelia. There are biases imprinted on this. And so the whole discussion about this planet now has devolved into this thing about, can we treat the observational biases or not? And how exactly do we do that? So let's have a look at this diagram. This is a map of the sky. It reminds me, that there is this thing called the Milky Way, shown in red. The Milky Way is a bad place to look for Kuiper belt objects. There's wall-to-wall stars, very hard to find Kuiper belt objects over in that direction. So there's the simplest example of an observational bias that affects this and other kinds of surveys. Now, I don't have a really strong opinion one way or the other. I mean, I'm sure that there's not compelling evidence for a planet yet, but there could be a planet. There's certainly room for a planet out there. I will just summarize the results of some papers. So Chad and Scott in 2014 said, hey, the objects look aligned. Could that alignment be real? So they were cognizant of small number statistics and they were cognizant of observational bias effects. Patigan and Brown came in and said, yeah, that's definitely real. We've discovered Planet 9, which I think is jumping the gun a little bit. I mean, a little bit too confident there. Shanklin came in and made a very nice description of the observational biases in their survey in particular. And their conclusion was, it's just observational bias. There's no reason to think that this supposed alignment of the orbits is real. And then Chad Trujillo came back with a review last year, 2020, summarizing all the work done since 2014. And his conclusion was, well, yeah, we still see that alignment, but it hasn't grown any more significant, even as we've increased the sample size. And so his conclusion is, well, yeah, maybe it's real, but we still don't know if it's real. So I think that's an appropriate conclusion at the present time. And then more recently still, people have started to come up with other explanations of why you could have an alignment. If there is an alignment, which is not established yet, maybe it doesn't necessarily relate to a planet. Lastly, let me just show this diagram. This is an observational diagram about, what can you see given a couple of different telescopes. So Pan-STARRS and LSST, excuse me, have these limiting magnitudes. Let's assume that LSST is about 25 and a bit. Then we would be able to see the Earth, the red line, to about 1,000 AU. With Pan-STARRS, we can see it to maybe 600 AU. Neptune, for example, with LSST, we could probably see to 2,000 AUs. And Jupiter, if we were lucky enough to have a Jupiter in the outer solar system, somehow, I don't think so, but if we were lucky enough to have that, we could see it to 3,000, 3,200 AUs. So we have pretty good optical sensitivity to distant bodies if we can do a good survey and go really faint with the LSST, which probably we can do in the next 5 to 10 years, something like that. So that's very exciting. And then I just mentioned there are other ways to do it. You can use thermal radiation. If you can go to appropriately long wavelengths, then you only have the inverse square law, not the inverse fourth law to worry about. You can use gravity. You can use the existence or non-existence of gravitational deflections from distant bodies to put limits on those bodies that might exist out there. But I think the bottom line is we'll have to see it in order to believe it. Okay, let's move on to Oort cloud. So Oort cloud, 1950, Jan Oort made the observation based on, I think, 16 long period comets that, first of all, the orbits have a very strange distribution of energy, binding energy, measured by the reciprocal semi-major axis. So that's plotted on the left. Zero means a zero binding energy. It means the semi-major axis is infinite. It's a body moving on a parabola. It's just not bound to the solar system. That tall peak is narrow, and it's a little bit to the right. So the comets in that peak are bound to the solar system because they're a little bit on one side of zero. There are basically no significant unbound objects in Oort's original diagram, although see the talk by Amaya to talk about two objects with eccentricities bigger than one. And Oort noticed that there's this tail going off to the right of bodies that have larger and larger values of 1/A. They correspond to smaller values of the semi-major axis. The other thing he noticed, which is now backed up by observations of many more comets, is that the orbits are isotropic. And so that's shown in the diagram on the right, where the dots are the directions of comets coming into the long period comets coming into the solar system. They're all over the place. North hemisphere, southern hemisphere, prograde, retrograde, they're coming backwards, forwards, all over the place. There's a band missing in the middle there for observational reasons, but they have an isotropic distribution. So he concluded that we are surrounded by a spherical swarm of comets that has a very large radius. And that radius turns out to be something like 50,000 AUs, which is about a quarter of the distance to the nearest stars. It's roughly a quarter of a parsec. Now, there are no good visual representations of Oort cloud. I found this thing on the internet that attempts to show the planetary region, the terrestrial planet region at the bottom with the asteroid belt. The Kuiper belt is that gray disk thing in the middle, and then that big, weird gray shape on the upper right is the Oort cloud. I mean, okay, but that gives you an idea of the relative scales. The Oort cloud is vast, absolutely vast, compared to anything else. So its significance seems to be that it's the source of the long period comets. These are bodies that were formed near the giant planets and then somehow emplaced out in the Oort cloud, vast distances. It is spherical. We think that's because of randomization by perturbations from passing stars. So initially it started like a disk. On a timescale of 1 billion years, it was isotropized, made into this spherical structure. It's really big, doesn't have a sharp edge, but basically if you go too far away, you can be detached by the gravity of other stars and the galactic tide. And so there's kind of a soft edge at about 50,000 AU. The bodies in the Oort cloud are all bound. They're all gravitationally attached to the sun. So they've been there for all of solar system time. And the width of that peak is very small. In fact, it's smaller than the typical scattering in energy space that you would get from a single passage through the solar system. So, when you get close to the sun, the gravity of Jupiter can pull you this way or that way. It can give you a little delta V, which corresponds to a little delta E. And that perturbation due to a giant planet is actually bigger than the width of the peak. And that means the comets in that peak have not been through the solar system before. So they're first arrivals in the inner solar system. So they were probably kicked out by some external perturbation from a passing star, and they've fallen for 10 million years to come in, and then we suddenly see them in the planetary region of the solar system. The ones in the peak are the first arrivals. Oort noticed that there are too many first arrivals compared to second and third and fourth and fifth arrivals, which appear over on the right-hand side of the peak. And he surmised that there must be some physical effect because his dynamical model failed to reproduce that. So there must be some physical effect, which he called fading, the fading parameter that explains that. And maybe that's true, maybe that's not true. The suspicion is that it's true. So it's spherical, it's big, it's bound, it's got that narrow peak, and there's some process that causes comets to fade after their first and second time through the planetary region. Somehow they're losing brightness, they're losing volatiles, we don't know. So there are basic parameters. We don't know the population very well. Population is order of magnitude 1 trillion, but it could be more, it could be less. We don't know very well because we don't even know the arrival rate of long period comets in the solar system very well. We don't know much about the sizes of long period comets. So therefore, we definitely don't know much about the mass of the Oort cloud. A good guess would be it's in the range from 1 to 10 Earth masses, but could be very much different from that. And the timescale for this, rendering the orbit spherical after their initial disky ejection, is about 1 billion years. So there are many, many hot topics connected with the Oort cloud. The two-step formation is pretty interesting. You have to kick it out of the planetary region and then circularize the orbits once it's gone out to large distances. Otherwise, it will escape from the solar system and go off into the interstellar medium, never to be seen again, or it will fall back into the planetary region to undergo another scattering event. So it's quite difficult to get the ejection and then that second perturbation from a passing star to circularize the orbit and lift the perihelion out of the planet region. And the estimates are that the efficiency of emplacement in the Oort cloud is between 1 and 10%. And so that means that for every object in the Oort cloud, there's somewhere between 10 and 100 that escaped, which means that interstellar space should be full of escaped comets ejected from our system and presumably ejected from the similar systems around other stars. And again, that goes back to Amaya Mora Martin's talk that either you can hear now or soon will be able to hear. There's one other thing, that when the solar system formed, we formed in a cluster, and it's possible for stars with comets over here to pass its comets to the star over here. So some of our comets might have been picked up from nearby stars. And in addition, perturbations from nearby stars might have been sufficient to circularize the orbits of escaping comets at much smaller distances than 50,000 AU, maybe like 5,000 AU. So we have this idea that there's a nugget, kind of an inner Oort cloud that could be very densely populated, but which is unobservable because the modern day stellar perturbations are not strong enough to erode it significantly. There could be an inner Oort cloud that's quite massive and quite important for understanding the origin and evolution of the solar system, but we can't observe it. And the truth is, we can't observe anything in the Oort cloud directly. It's all too far away. It's all magnitude 38. It's like crazy faint, it's crazy distant. And so all we can do is infer the properties of Oort cloud from objects that have come into the solar system recently from the Oort cloud. I'm going to skip over this. I just thought I'd put in an observation to show you that research on Oort cloud comets is current and exciting. This is an area of mystery where observations can make a big difference. But I think to save time, I'm just going to skip over this and refer you to the papers mentioned at the bottom. So lastly, let me just talk about birth constraints. What can we say about birth constraints on the solar system? Well, this was summarized in a very nice paper by Fred Adams about a decade ago. And the observation is right there that stars form in clusters. So you look in the sky, you see Orion, you see the Pleiades, you see the Hyades. These are clusters of young stars. Stars in general form in clusters because the Jeans mass for the interstellar medium is many, many times, typically hundreds or thousands of times the mass of a single star. So they have to form in groups. And then those groups disperse under some initial velocity dispersion. So the sun probably formed as a member of a group. What can we say about that group, that birth cluster, from physical measurements of the solar system? So I'll just very quickly go through this. We know that the solar system has had in the beginning a significant component of incorporated aluminum-26, which is this very powerful radioactive element, decays with a timescale of 700,000 years or something like that. The half-life is 700,000 years. So that means that the aluminum-26 was produced and released from a massive star shortly before the solar system formed. And that's interesting because right now there are no massive stars near the sun, and that's because massive stars are rare, and that's because they don't live long. The lifetime of a star varies inversely with the mass to the power of 2.5 or 3 or something like that. So the big stars basically just explode. And so that itself is good evidence that we were in a cluster that was big enough to contain a 25 solar mass star, which exploded and seeded us with aluminum-26. Whether that explosion caused the collapse of material around the sun, we don't know. But there was a massive star near the sun as the planetary system formed. On the other hand, we know from the size of and the stability of the planetary region that probably no star has been closer to us than 100 AUs. So that sets a constraint on the density of stars and the amount of time for which the sun has been in this cluster. We know that there's this edge to the classical Kuiper belt. Now, I personally think it's got much more to do with the 2-to-1 resonance than with any passing star. But if you had a stellar encounter, at 200 AU, then you could conceivably truncate that disk at 50 AU, like that. So that may or may not be a constraint on the stellar density near the sun and near the planets when the whole thing formed. We see detached Kuiper belt objects. Maybe they were in place, maybe they were detached by a stellar encounter with a distance of something like 400 AU, but maybe not. Maybe they're more related to unseen planets or just unseen massive objects, Pluto-like objects in the Kuiper belt or something else. But that's a possible constraint on the Kuiper belt, on the origin of the solar system. And then we know that the giant planets were not photoionized away and ablated down to little nuggets. So that sets an upper limit on the flux coming into the solar system from UV-rich, highly massive stars. So the point is we have various constraints from physical measurements of the solar system. And put all together, Fred Adams concluded that we can constrain the product of the density of stars, number of stars per cubic parsec, and the amount of time that we were in that cluster as a product. So N1 delta T is like 80,000 per cubic parsec million years. And the number of stars, you have to have about 4,000 in order to have the probability of getting a massive star to produce the aluminum-26. If you didn't have many stars, you wouldn't have any chance of having a massive star, given the mass distribution of the stars. So for example, you could have 4,000 stars in a single cubic parsec for 20 million years, or 4,000 in 10 cubic parsecs for 200 million years, that kind of thing. You can do trade-offs. And it allows us to say something about the birth environment of the sun. Okay, so that's all I wanted to say in this first lecture. I'll come back soon and we'll talk about the middle solar system. See you then.